everybody. I'm going to be talking about making primary and secondary alkyl halides from primary and secondary alcohols in this video. So there's a couple of handy reagents that can help us go from an alcohol to an alkyl halide, which is going to be really helpful synthetically when we're looking at starting with an alcohol, which is often very easily purchased. You can also make alcohols in a variety of different ways, and then being able to turn those into a really good electrophile with a good leaving group and everything. So the two reagents that we're going to talk about the most here, thionyl chloride, which is SOCl2, is where you'll often see it written on over an arrow is going to be SOCl2. It has this structure. This is going to make alkyl chlorides for us. And then phosphorus tribromide, that's PBr3, and that's going to be making alkyl bromides. So the thing we want to keep in mind with both of these is that they're really nice examples of SN2 reactions. Okay, so we want to keep in mind that all of the same rules of SN2 apply. Okay, so we're thinking about inversion of stereochemistry. We're thinking about no reaction on tertiary alcohols. Okay, all the same kind of SN2 style rules are going to be applying here. So let's look at thionyl chloride first. Okay, I'm just going to write SN2 as many times as I can on this page for us to really get that in there. Okay, so I'm going to start off with the secondary alcohol here. I've got my OH on a wedge. So that secondary alcohol, I'm going to have that react with thionyl chloride. And the other reagent that you'll often see paired with the thionyl chloride is pyridine. Okay, so we want to keep in mind here, like the pyridine is a base. Okay, all it's there for is to act as a base and make sure that this reaction doesn't get too acidic. And you'll see why as we go through. The thing that I want you to be very, very clear on, though, is that this pyridine is not basic enough to deprotonate that alcohol. Okay, the pK of this, the pyridine nitrogen, if you protonate that, that's going to be a pK of about 9, whereas this alcohol pK is about 16. Okay, so there's no way that we're using this pyridine to deprotonate it at the start. Okay, we will get to something that eventually is much, much more acidic where our pyridine can come in, but for right now, it is not acidic enough, or the OH is not acidic enough to be deprotonated by a fairly weak base like pyridine. So our very first step here is going to be a nucleophilic attack from our alcohol onto our sulfur. So we're kind of thinking of the sulfur as a delta plus right here. So we can have our lone pairs come in. And this is a little bit different than what we've seen in the past, because normally we just kind of think about that chlorine getting popped off. But whenever we have an oxygen double bonded to some atom, like a carbonyl, or in this case, the sulfur to the oxygen, those electrons are going to first move up onto the oxygen to form a tetrahedral intermediate, and then they're going to come back down and we'll lose the chlorine. So this mechanism is slightly different than what we've seen in the past. I'm not going to be expecting you to be able to replicate this mechanism on an exam or anything, because it does not quite fit with the rest of the material that we're covering so far. But I do just want to make sure that we understand how this is working, and this will be very applicable to reactions that we're going to cover in second semester. I'm talking too much and I'm not paying attention. Okay, here we are. Okay, so we have our tetrahedral intermediate. We've got the alcohol connected, the O-, and then the 2 chlorines. So now we're going to see those oxygen lone pairs come down to reform that pi bond. And we're going to lose one of those chlorines as a leaving group. Okay, so now we end up here. So this is where the pyridine actually comes into play. So now that we have this H on that oxygen, it's much more acidic now. So the pKa of this species is about -2. So now we're in a much better position for the pyridine to be a strong enough base to be able to deprotonate what is now a very acidic proton. Okay, so we're going to bring in our pyridine. It's going to grab that H, give the electrons back to the oxygen. Okay, and then we have that as our conjugate acid. Okay, so now what we've essentially developed here is that this group is now a very good leaving group. Okay, so we started out with something that's a fairly poor leaving group and just OH minus, but now we have something that when we attack with our chlorine or chloride, so our chloride is going to come in, do our SN2 attack, so we're going to attack from the opposite side, and then this can go form a pi bond to the oxygen sulfur, and then kick off our other chloride. And what that's going to do is we're first going to install our chloride in the back. We're also going to be making SO2, which is a gas. Okay, the best leaving groups are gases because they just come right out and pull the equilibrium towards product. And then we also made more Cl minus. Okay, that Cl minus is what's going to be hanging around with your pyridine. Okay, so you're going to be forming a pyridinium chloride along the way. Okay, so again, this mechanism, I'm not expecting you to know it, but I do want you to keep in mind that we do have an SN2 process happening right here. And I think knowing that SN2 part is happening is really helpful when you're trying to predict the products and think about inversion of stereochemistry and all that. So just want you to keep that in mind. Okay, and not make it so black boxy that you don't know where it comes from. Alrighty, so let's look at the phosphorus tribromide. Okay, also SN2 here. So let's use the same substrate. Just use our secondary alcohol. And for this one, we just need PBr3. Okay, so we've got our phosphorus tribromide. I don't know why I keep doing that. Okay, again, that phosphorus is going to be our delta plus because I've got 3 bromines attached to it, so it's pretty delta plus. And I'm going to have my OH come in as a nucleophile, attack that phosphorus, and then that's essentially going to be one SN2 reaction because I'm going to kick off a bromine here. Okay, so I want you to keep in mind that since that OH is acting as the nucleophile here, nothing is happening in terms of that carbon, right? That stereocenter is remaining untouched. So I'm ending up at this intermediate, and I've also created a bromide, okay? So my bromide is now going to be my good nucleophile. So we're going to have that bromide attack the carbon, kick that off, because now I again have another good leaving group that I've created, okay? So the two things that these reactions have in common here is we're really starting with an alcohol, which is not a very good leaving group, and then we're transitioning it to become a good leaving group, and in the same process, making a good nucleophile along the way. Okay, so in this case, we made a bromide. In the thionyl-chloride instance, we made a chloride. So we have two good nucleophiles that we're choosing from. So we're making a better leaving group and generating good nucleophile. This is our second SN2. This is the one that actually gives us inversion, because now it's happening on that carbon stereocenter. Okay, and we get the HO-PBr2 as our byproduct. This can still keep reacting until we have 3 oxygens and no bromines on there. But we have that product. And remember, we're going to look at inversion. Because again, SN2 process, okay? So just as a kind of sum up here, these are governed by SN2 reactions. We first make a good leaving group. We generate good nucleophiles, right? So we'll label our nucleophile. Okay, so chloride up in the thionyl-chloride case generated a good nucleophile over here with bromide. Okay, and so we're looking at good leaving group, good nucleophile, we get alkyl halides out. Okay, and I'm just going to write this at the bottom here so we have it top and bottom. Neither of these work on tertiary alcohols. Okay, so we just want to really, really keep that thought in our mind. If I've got something like this, if I try to use PBr3, no reaction. If I try to use thionyl-chloride and pyridine, no reaction. Okay, so we're not doing SN2 reactions on tertiary substrates. Okay, all right, so as always, let me know if you have any questions and I'll see y'all later.